So let's take a look at this question found on page 200 of your Nelson 12 book. I think it was question number 13. Several of you have been asking about this particular question. Not quite sure how to solve it. Just to let you guys know, this is actually pretty similar to a question that we solved in the previous lesson. So I'll see if I could tackle it the same way. So when I talk about the law of conservation of energy, that really is no different than the work kinetic energy theorem. They're actually the exact same thing. I guess just looking at things from a different equation perspective. So what I'm going to do is to solve this question. First of all, let's analyze what's happening. So the 22 kilogram filing cabinets right over here. We do have a normal force acting up, a force of gravity acting down. These two, as you guys all know, must be balanced since the cabinet does not accelerate up or down. But we know that this clerk is pushing with a force of 98 newtons in the forward direction, and there's a force of 87 newtons friction acting in the direction opposite to that of slippage. So here's the thing. Obviously, there is work being done on this filing cabinet. So what I'm going to do is I'm going to state that the total work that's being done on this filing cabinet must be, well, by definition, work is a transfer of energy. And in this case, it is a transfer or a change in kinetic energy. So let's take a look at the total work that's done. Now in this particular case, I know for a fact that the applied force and my force of friction are constantly going to be acting on the filing cabinet the entire time, from the beginning till the end. What that means is if I take a look at the total work that's being done, I could actually state that the total work is a result of the net force acting on the object itself multiplied by the total displacement that it moves. And if you take a look at the right side of the equation, it's your change in kinetic energy, which is of course your final kinetic energy, which I'll write down as 1/2 mv2 squared minus my initial kinetic energy, 1/2 mv1 squared. Now here's where things are going to be made a lot simpler. We all know for a fact that this filing cabinet does in fact start from rest, which means that its initial velocity, or its initial speed, should be 0, which means that if your initial speed is 0, your initial kinetic energy must now be reduced to 0 as well. And now the equation becomes fairly simple. So let's take a look at the left side of the equation. We do have our net force, which is of course the sum of all the forces acting in this case, the horizontal plane. So we have a 98 Newton force acting this way, 87 Newton force acting that way. You guys do the math. I believe it turns out to be I believe it turns out to be 11 newtons for your net force. We know for a fact that it does move 1.2 meters in the forward direction, and all of this got to be equal to 1/2 times its mass, 22 kilograms, times its final speed squared. Okay, so let's just do a quick little calculation on the good little calculator here. I'm not really good at math, but let's just try anyway. 11 times 1.2. What does that give me? 13.2. Very nice. 13.2, which equals half of 22, which is 11, times your final speed or velocity squared. So if I just move really quickly and find out what my final velocity turns out to be, I end up with an answer of about 1.1 meters per second. And there you have it. Okay, if you have any questions, just ask me on ask me on Edmodo. Okay, wonderful. Everyone have a good night. We'll talk to you on I'll talk to you tomorrow for tomorrow's lesson. Okay, bye.